Welcome to the Health AI Brief, breaking down the AI shaping our world one concept at a time. Every time you calculate a Q-risk score or look at a prediction for ICU length of stay, you're interacting with the grandfather of medical AI, regression. And before we get seduced by neural networks and deep learning, we have to understand the statistical bedrock that underpins 90% of the clinical risk models currently used in hospitals. The fundamental question these models answer is relatively simple. It's asking, are we predicting a continuous number or a specific category? So let's break down the two main players that there are. So first, there's linear regression. Imagine a scatter plot of patient data, let's say systolic blood pressure versus age. Linear regression simply tries to draw the straightest line possible through these dots. It minimizes the distance between the line and all the data points. We use this when the outcome is continuous. If you want to predict exactly how many units of insulin a patient needs or how many days they'll stay in the hospital, you're using linear regression. But medicine's rarely about continuous numbers. It's often binary, sick or healthy, discharge or admit, alive or dead. This is where logistic regression comes in. Instead of a straight line that goes off to infinity, it fits an S-shaped curve to the data. It takes your inputs, things like age, troponin, history of smoking, and squashes them all into a probability score between 0 and 1. If the output is 0.8, there's an 80% probability of the event occurring. This is the engine behind well-known things like the Wells score, CHA2DS2-VASc, and almost every mortality predictor that's used in practice. So why does this matter to your practice, and what are the limitations? The massive strength of regression is transparency. It is explainable. You can look at the equation and see exactly how much weight is assigned to age versus creatinine. You can explain to a patient why their risk score is high. The weakness is that it assumes linearity. It assumes that as age goes up, risk goes up at a constant rate. But biology isn't always linear. Sometimes risk skyrockets only after a certain threshold is reached. Regression models often struggle to capture these sorts of complex nonlinear interactions that a human doctor may spot instinctively, and which some of the techniques that we'll come to in future episodes are more adept at handling. So when you're appraising a paper, if the researchers used logistic or linear regression, that's a good thing. It's a very explainable, straightforward tool, and it means they chose a robust, transparent tool. Don't let them hype it up as cutting-edge AI, but respect it as a gold standard for evidence-based medicine. So that's regression in a nutshell.